It's a great pleasure to introduce the next speaker, BART WESTERKAMP from Alkmaar, Netherlands. Now, what qualifies BART WESTERKAMP to address this prestigious audience? Simply speaking, because he's an ingenious engineer who has understood at early stage that meaningful biomedical progress will only be achieved when engineers and physicians join forces. Now, many clinicians, including myself, are talking about the future anesthesia machine, but BART WESTERKAMP is the man who has made it happen. He is the man and the brain behind the legendary Physioflex, the world's first computer-based, closed-loop, feedback-controlled, closed-circuit anesthesia workstation and pulmonary function lab. With the Physioflex, BART WESTERKAMP has eliminated ghosts of the past, like common gas outlet, user-adjustable fresh gas flow rate, outer circuit vaporizer, and the scrambled monitor screen, which was cleaned up in the Physioflex. Eventually, volumes were precisely determined. Anesthetic vapors could be removed from the circuit completely and not by high flow, diffusion, dilution, and environmental pollution. Oxygen uptake was no longer a matter of speculation, but a matter of measurement, and xenon anesthesia became clinical reality. In short, I have 60 seconds. BART WESTERKAMP is the Pontifex Maximus, bridging the gap between applied physiology and advanced technology. But we are curious to listen to what you're ready to share with us. Thank you.
Okay. Thank you very much. I found it an amazing honor to be here as an engineer to talk a little bit about applied physiology and how we transfer that into an anesthesia machine. And I come from Alkmaar, where the cheese market is, and you see jumping in NAVAt with a gate. And the gate is the symbol of Alkmaar, which was able to kick out the Spanish in 1572. I have a conflict of interest because I'm still an advisor of the Vitacoop project. I will show a few pictures or give you some information of this new development, which is now the end stage and is going to apply for CE. Well, I took the name of a publication I made in the past together with Professor Eerdman, Closing the Loop from Sensor to Therapy. And that's my passion. I started in 1982 to understand what closed system is, and until now it really has been my passion. And some time ago, an artist from Rotterdam made this image of closed circuit anesthesia and the impact on humans. He made a little mistake because the red here is too small, but that is the oxygenation of the blood. But the P is from the physiology, and something you can hear is the human body, and this is the recycling of the gases. Well, it all starts with spirometry, and that links very much to what Jörn has been telling us. To understand what's going on there, you have to understand what spirometry is and what's happening in the lungs. And it's very old, because this guy, Claudius Galenus, already did some measurements on lung volume with a goat bladder on young people. And he described that, and his knowledge was used until about 1500. So that was quite amazing. Well, Hutchinson did for the first time a big study on lung volumes. And he reported 2,130 measurements in humans. And then Tussaud did improve the system. He could really record it, And that remains for about 50 years the golden standard. Then, this was something I found out later, but Dennis Jackson published in 1915 his anesthesia machine. And if you, as a technician, really look into that, is that that guy must be more than a genius. He uses a circulator to circulate the gas to have a constant concentration all over the system. There are no valves involved. He found a system to eliminate CO2. He administered oxygen or nitrous oxide, and he calculated more or less what the oxygen uptake of the patient was, and he had the gas going through the balloon, and then you could ventilate the patient, but you always had a constant concentration of gases. He tried. And the most important thing is this: he had an amount of volatile anesthetic in it, and it was ether or something else. I don't know what he used, but at least ether. And he just calculated how much ether in volume the patient needed to get the required partial pressure in the brain. So he didn't dose on concentrations, but on volume. Well, of course, there were some concerns. He couldn't measure oxygen uptake. And the reservoir back near the patient was also very heavy. But as looking as a technician to this solution, the man was really great. Ralph Waters, more known about this system, actually simplified his idea. And what was very important was the absorption of volatile anesthetics in a closed circuit by charcoal. And first it was used in the mining industry, but Epstein was the first one who ever applied it. And Revel made the to-and-fro system of Waters with a circulator. And he did that because he wanted, at his children he was operating, he wanted the best and stable concentration of his gases. So it was not piece by piece going through the circle. No, he had circulating the gas to have it. And Ross made a feedback control system in 1983 to administer volatile anesthetics. Well, all these developments have their value. So now I'm going to look into the standard closed, semi-closed circuit. And everybody assumes that you can run closed with it. Well, what is the process of a modern closed system to get closed? Is you reduce your fresh gas flow from low flow to minimum flow, that you have a fresh gas flow where the uptake flow is the patient's oxygen uptake. And if the fresh gas flow will near the patient uptake, it's closed. That's the consideration. Well, then I have some questions as a technician. How will patients' oxygen uptake be estimated? It's just guessing. When is the semi-closed system totally closed? Well, when all elements of the process are constant FRC, constant cardiac output, yes, then you can travel closed. To me, this technology will not meet the requirements of totally closed. Will totally closed be possible in a semi-closed system? Well, this is an old picture everybody knows about uptake of gases. And you can see that your fresh gas flow in the early minute is completely different from a few minutes later for your volatile anesthetic. In this case, nitrous oxide, but if you would apply xenon, you have the same problem. But there are all kinds of disruptions. You have a very high fresh gas flow needed in the beginning, where the fresh gas flow is higher than the patient uptake. And surgeons may cause shifts in FRC, and also airway problems can do the same. Leakage of reduced fresh gas flow results in an empty system, which you don't like to have. and the desired inspired oxygen concentration will fluctuate. It will never be a straight line. So the oxygen uptake of the patient will vary due to physiological and pharmacological effects. That's also a problem. So any change in the gas mix and VA was out needs an increase of fresh gas flow. And then you're not closed. In 1976, Wilhelm Erdmann at the World Congress in Mexico presented his philosophy on control and management of closed ventilation systems. Lung and mechanical ventilator system must be considered as being one system. And if you see as a technician into this, it's very logical. Because what goes in must go out if you want to keep the volume constant. And if you keep the concentration constant, then if you give too much in, it will explode. If you give too little in, it will implode. So if you can keep that constant, you meet with those requirements. What does his philosophy means to gas management? I will try to show you how it actually works. So you maintain the oxygen concentration in this system constant. So I've uptake and I've got my dose. To be sure that the concentration in my system is constant, I circulate the gases at 60 to 70 liters per minute. There's a nice idea behind that of time constant and so on, but that gives you then a really good inspiratory concentration. And you need to keep this volume constant. But you give also, on this level here, you want to ventilate the patient. So you have a ventilation, but basically the volume remains the same. Now when I get oxygen uptake, so my inspiratory concentration is smaller than the set because I have an oxygen uptake. So to keep that volume constant, I have to give an oxygen dose, and then my oxygen concentration remains constant, and so do my volume. So if I have, for instance, as a carrier nitrous oxide, then also nitrous oxide uptake will happen. Now the system constant, the volume shall reduce. So to this level. But if I give a dose of nitrous oxide, then it goes back and I have my volume again constant. So now I know oxygen uptake, I know the uptake of nitrous oxide, and also if I do the same kind of theory, I know exactly how much I administer for volatile anesthetics or xenon or whatever. Actually, it's not rocket science, it's very simple. If I have a leakage, what happens? Well, I have my uptakes here, I have superimposed my ventilation, I get a leakage. Nothing happens because the ventilation will be superimposed on it. So I never get an empty system because every leakage will be compensated for the volume. So I have my ventilation always superimposed on the fresh gas flow of the leakage to compensate in my uptake. So even if I've got a leakage, no sweat. The system remains filled, my concentrations remain the same, and it's no problem. Well, the clinical needs for the technology to realize the system is very known to everybody. You want to have the PCO2 at a normal level. The oxygen uptake covers the cell's demand. It was Mr. Plieger in 1872 who really stated that as a German physician. He said, it just concerns the cells. They define the uptake of the oxygen and not the other things. That's the consequence. You want to have a SpO2 above 95, your FiO2 at a desired value, and an uninterrupted CO2 elimination. And no overinflating of the lungs, eagle ventilation of all lung compartments to obtain minimal shunt. like Göran already applied for, and we realized it in this machine. A swift and controlled washing of volatile anesthetics, and also preventing airway irritation with Desiree, for instance. Entitled control of volatile anesthesia and easy removal of only volatile anesthetics. Well, the first time we did something was in 1983. It was also published in a book, and actually we grabbed, I worked at that time for the Meinhardt company, we grabbed some parts of different equipment, and we built the first system. It was only controlling oxygen and nitrous oxide. You couldn't do anything else, but we measured the volume with a dry rolling seal, and based on the information, if there was loss of nitrous oxide, it administered nitrous oxide, and the oxygen was calculated on the inspiratory oxygen concentration. It was used, oh, that's too far. It was used at the University Hospital and also in Sportkliniken Hellesen in Ludenscheid, where I was introduced in doing closed circuit anesthesia on the Dro machine. In 1987, we started with the Rotterdam anesthesia ventilator. In the book of Eisenkraft from 1993, you will find everything about it. And it was used in 3 hospitals. One of them was in the University Hospital in Ghent by Professor Rolly, who could check our wash-in of gases and wash-out of gases with his mass spec. And I must admit, we thought we did it quite well, but if you look with the mass spec, then you find little things. And you find things which are not mentioned in the textbook. That's also very nice. So out of that, we developed the Physioflex, which was produced from 1991 until 1995, and it was sold in those countries. Specifically, South Korea was very interesting for us. We were, at that time, we owned the company. I forgot to tell the guy with the narcocon, that was Geert van Dijk, and as a matter of fact, we are both the inventors of the Physioflex. I did the physiological, technological part, and he did the technological into software and everything. And then Draeger took over the whole thing, and the machine was sold until 2000. Because then they had a new machine on the market which would be much and much better. And what benefits this philosophy? Well, you have an inspired oxygen uptake which is constant. You never have to think about it. The next development we have, you can even set your inspiratory xenon concentration, and it will be kept constant. You have a system volume control, so you have never an empty system. You will never have to use your flush button because it always will be filled. There's a separation. You have a primary where you ventilate to the secondary part where you have the patient gas. And it has to be really closed until 50 millibar, and you will not have any leakage bigger than 10 milliliters per minute. Because you want to be able to measure oxygen uptake even of neonates. And the bag, the manual bag, never contains patient gas, and the inspiratory temperature after about 10 minutes, Wissing published about that, will be always be between 34 and 36 centigrades, and the relative humidity above 90%, because the CO2 absorber produces quite a lot of water. So each gas is independently controlled. I will show you later, and we could give a maximum of 30 liters per minute because the standard requires that, but you never use it. And quantitatively liquid injection to control the agent inspiratory or entitled. And we have an oxygen uptake direct measurement, and the total amount of administered gas or AC is measured. So, to give you an idea, after washing, you have a 6 milliliter isoflurane used over 3 hours, which is very, very little. And xenoablation, to give you a 9.5 hours, 23, so that means you've got 42 hours, 42 euros per hour, which is not a very high cost price for xenon anesthesia. Removal without disturbance via CO2 elimination uninterrupted. So you could use the system for over 24 hours. You do that by 2 absorbers, one is always on, in, and one is out. You can change, and you can just switch over. The agent elimination by charcoal and the ventilation independent of the fresh gas flow. And if you rinse oxygen, you use an oxygen flow of at most 5 liters per minute. But that's all computer controlled. Well, this is the Physioflex. And I very briefly will go through the technical solutions. You have no valves in the circuit, and you circulate the gas with a circulator, so you have 70 liters per minute. You have 4 membrane chambers, 1 for the smallest patient, and the larger you need 4 in parallel. You have a sensor for pressure and temperature sensor. You have analyzers. You have a paramagnetic oxygen analyzer. You have CO2, nitrous oxide, and volatile anesthetics. Side stream, but the sample is fed back into the system, so it always remains closed. And it's not shown here, but in parallel of the oxygen analyzer, for xenon, there would be a xenon heat conductivity sensor. The gases here, there was a vacuum used to rinse the system. You had compressed air, nitrous oxide, and 2 dose valves for oxygen. So if one failed, you always could give oxygen. So that was already redundant. From 1979, 97, xenon was available. Volatile anesthetics were injected by a glass syringe, and we had a selection valve. So there were 3 bottles connected to the system, and you could select which one you want to use. Then the syringe was filled and injected into the system. You had 2 CO2 absorbers, as you can see here, where you could switch over. You have an integrated charcoal filter, and that was a limitation because, as you know, desflurane boiling point is about 21 centigrades. So charcoal you can't use at room temperature. You can use it, but then you need a huge amount because the difference between the gas forming desflurane and the liquid desflurane is a factor of 200. So you need 200 times more of charcoal then. That is technically impossible. You had proportional valves for inflation and expiration control. So what Jörn was already applying for, have an expiratory control of the flow control of the expiration. We already implemented that in 1996. Then you had here your handbag. By switching over here, you could manually ventilate the patient. And we did already do something about safety. We had a garden unit measuring the inspiratory oxygen concentration, the ventilation, and the volatile anesthetics. And if it was over the limits you have set, it was a separate system with a separate microprocessor, and it gave you an alarm. Now this is a very nice picture to give you an idea. I hear always 100% of oxygen to inspire. It's impossible. You have 30% of oxygen, okay. Then I come to 62% of nitrous oxide, but I have 37 millimeter of mercury water vapor, which is about 5%. So, oh, that's too far. So in the end, you only have 3% of nitrogen in your system. And here you can see that you have your tidal volume here is completely independent on the fresh gas flow. So here it's about almost about it's over 7 liters per minute, and nothing actually really happens. Volatile energies and tidal controlled. Well, this is a very interesting thing. At this moment, this girl started to bleed, and so the anesthesiologist raised it again because the volatile anesthetic was washing out of the body. But with this system, it doesn't care. It replenishes everything which is left the body with nitrous oxide or volatile anesthetics, because we just controlled on the end tidal level, so it doesn't matter. And you can see here this short rise, and then it's flattening here. And then she went back, because I said, you don't have to rise it. And you can see that it really works very well. Will this technology end? No, certainly not. We have now under development this machine, which goes more and more further. It has not only a measurement of oxygen uptake, VCO2 and respiratory quotient during your anesthesia. What do you want more? Well, I'll give you some idea how the technology improved. We started to ventilate with the Oxyclock 1000, then we used compressed air, and now we use very special thing, a high performance blower, which was developed actually by Geert van Dijk, my former partner. And we can do amazing things with that thing. We started with this rolling seal, then we had the membrane chamber, which just moved up and down. And then we started with this technology I developed, and you will see, then if you put it back, so it's closed, and there is no glue in it. This is a very special technique where you, where the whole system remains closed, although it's free movable. On safety, we go very quickly. Now we have complete redundancy. Hygiene is very important. That was difficult. And now we have a devisable circle which you can put in the washing machine. Agent administration first with a syringe, then with this one, and now we use dosage pumps. And this goes container. I have to hurry up. Xenon. This is xenon, and they used a closed spirometer to do it. This was the first anesthesia given by Rob ten Brink, and it was in October 1997. And on this machine, the whole what do you call it? Studies of xenon to get European approval was done. This is another time of, and you can see you only use very little of xenon over that time. This is where you see something about oxygen uptake, but that would be too much. How can we do it? Well, I mentioned already Professor Rolly from Ghent, and Jan Peter, his contribution was that I learned exactly how to measure oxygen uptake in his laboratory. And there actually were 4 key persons all over the time, besides of me. That's Wilhelm Eertman, Rob ten Brink, Jan Hofland, who isn't here, and Geert van Dijk, who also grew a little bit older, and of course myself. Jackson failed because sensor computers. Well, this is what I just told you about. Why can you do this? Well, now you all do this, manual control. And this is the future, process management. And that means that the physician may change from anesthesia device operator into process manager in optimizing patient treatment. A paradigm shift. Thank you very much.